Good afternoon. I'm Jay Scott, editor of ASHRAE Journal. Thank you for joining us for today's webinar, part of the Journal Supplier Webinar Series, providing information to readers and others about products and technology for industry professionals. ASHRAE does not review supplier webinar presentations. Mitsubishi Electric Trane HVAC US presents today's webinar, Applying VRF and Third-Party HVAC Systems. Today's presenters are Kevin Miskowitz, Director, Commercial Product Planning, and Tom Greco, Director, Solutions Business Development at Mitsubishi Electric Trane HVAC US. And now we turn the webinar over to Kevin. Thank you.
Thank you, Jay. Good afternoon to those joining us on the phone, and welcome to the Applying VRF and Third-Party HVAC Systems webinar. Tom Greco and I are excited to spend the next hour discussing the HVAC industry, and more specifically, an introduction to integrating variable refrigerant flow systems with third-party HVAC systems, along with sharing a real-world example of a successful application. Today's webinar will cover the following topics. Understand why VRF systems are positioned to be the primary heating and cooling technology of the present and future. Discuss why VRF systems are applied with existing and complementary HVAC equipment. Understand how VRF manufacturer controls and services facilitate integration and solve building challenges. And at the end, we'll share an example of a successful VRF and third-party HVAC system application. We'll leave plenty of time for questions at the end of the presentation and look forward to answering them for you today. Be sure to submit them throughout the presentation by using the Q&A function within the presentation software. VRF technology has been in use around the world for over 3 decades and is the prominent and oftentimes default HVAC system of choice. Its worldwide popularity is largely driven by the high cost of energy, tight construction requirements, and limited space for mechanical equipment within a building. In fact, VRF systems can make up 80% or more of the HVAC systems applied in places such as Europe, China, and Japan. In the U.S. market, sustainability-driven legislation, utility incentives, and innovative design concepts such as strategic electrification that seek to significantly reduce our dependence on fossil fuels are increasing the demand for an electrified built environment. That environment is ideally suited for VRF systems. VRF systems are often applied with existing and complementary third-party HVAC equipment based on the specific needs of a building. It is imperative that VRF manufacturers provide controls and services that streamline management of those systems, which ultimately minimizes the headaches that come with system integration. Before we dive into the concept of pairing VRF with third-party HVAC systems, let's take a step back and go through a brief overview of VRF technology. Instead of moving conditioned air through ductwork to the space requiring conditioning, VRF delivers conditioned refrigerant directly to that space, eliminating the requirement for long runs of ductwork within a building. This eliminates the inefficiencies that come with moving conditioned air a long distance through those ducts and provides a more energy efficient, quiet, and flexible way to condition a space. Inverter-driven compressors within the outdoor unit vary their speed to meet the conditioning demands of a particular space. This leads to less energy waste within the system as the compressor modulates instead of continuously turning on and off, which is a very energy-intensive process for the HVAC system, as we all know. The result of those two items, among others, is an energy-efficient HVAC system that doesn't sacrifice occupant comfort. Speaking of occupant comfort, VRF provides the ultimate personalized comfort experience for a building's occupants. Each space or zone requiring conditioning will have their own network of indoor units. This network of indoor units is controlled from within the space, providing the occupant with the ability to personalize their comfort. This leads to happier tenants and fewer comfort control complaints for building owners and facility managers, who we all know appreciate that. In addition, due to the design flexibility of VRF and its overall smaller footprint, it can be applied to a variety of building types and applications. From adding capacity to an already taxed HVAC system on a college campus, to providing a K-12 school with a quiet, efficient way to cool classrooms, to conditioning a new high-rise new construction project, VRF is the optimal HVAC choice. At its most basic, a VRF system consists of an outdoor unit connected to a network of indoor units through refrigerant piping. The system's operation is governed by a network of controls, which read data from a variety of sensors located throughout the system. Depending on the needs of your specific application, VRF systems can be applied as heat pumps or heat recovery systems. Heat pump systems operate in all heating or all cooling, depending on how the majority of indoor units are calling. These systems are ideal for applications where temperature consistency across a building or a space is common, such as a larger open space within a school or an open office concept, which we all know and love. Heat recovery systems provide simultaneous heating and cooling operation from the same system. These systems utilize a branch circuit controller, which acts as a means of transferring heated refrigerant from zones in cooling to those zones calling for heating and vice versa. Simply put, it can be seen as a traffic cop or a traffic direction for that refrigerant. Heat recovery systems are ideal for applications where individual temperature requirements vary by occupant, such as individual offices, conference rooms, assisted living facilities, classrooms, or hotel rooms. VRF systems can also be applied in two configurations: air source and water source. Air source systems use air as the heat transfer medium, expelling rejected heat into the air outside of a building. Water source systems use water as the heat transfer medium, expelling rejected heat from the space into a water source typically located inside the building. You can even tie water source systems into a geothermal loop system, which further maximizes their efficiency due to the relatively constant underground temperature of the water loop. Both configurations, air and water, help maximize energy efficiency for the building owner. As today's buildings become more complex, the challenges associated with their construction and operation are on the rise. One challenge that all buildings face is energy efficient operation. The demand for sustainability has pushed the AEC industry to move towards designs and standards that reduce overall building load and energy consumption, along with carbon emissions. VRF systems are equipped with variable capacity compressors that heat or cool low load environments with less likelihood of short cycling. This is especially helpful in those more tightly designed buildings. In addition, VRF systems are electric powered and do not require the use of fossil fuels. This contributes to the strategic electrification movement and helps the country reduce its overall reliance on fossil fuels, along with reducing the carbon emissions for the building owner. I just mentioned strategic electrification. Let's spend a minute digging into what that means. Much of the drive towards building modification and modernization comes from two types of programs, voluntary and policy-driven. Here are two programs that are leading the way in that regard. On the voluntary side, we have the 2030 Challenge. This program aims to reduce carbon emissions by driving towards carbon-neutral buildings by 2030. Leading architecture, engineering, and construction firms have been committing to designing and building more sustainable buildings and along the way, reducing greenhouse gas emissions. In fact, the challenge has gained popularity and has now become standard practice at some of the leading AEC firms across the United States. New York City's Local Law 97 is an example of a policy-driven program. This benchmarking law requires properties larger than 25,000 square feet to report on annual energy and water use. Building owners will be fined if the carbon dioxide emissions produced per square foot exceed the limits established for the specific category of building. Laws like this will further drive that push towards electric-powered systems and away from mechanical systems that consume fossil fuels, such as natural gas. Strategic electrification is a concept to get to know, as we'll see it more and more as we head into the future. In summary, VRF systems are an energy-efficient and flexible way to solve a building's conditioning challenges, while not impacting occupant comfort and design friendliness. In addition, VRF systems can easily be paired with other third-party HVAC equipment, further increasing their flexibility and application. Now that we have a basic understanding of VRF, I'll turn the presentation over to Tom Greco, Director of Solutions Business Development at METUS, for a deeper insight into the world of third-party integration. Tom?
Thank you, Kevin. Excellent job as always. Thank you to everyone else on the phone for joining us today. After that overview, we're going to now dig into some of the technical aspects of how standard VRF controls get integrated into a building's infrastructure when third-party equipment is also in the picture. As we noted earlier, because of the efficiency and overall demand of modern buildings for VRF technology and third-party equipment, more of today's buildings are requiring an integration between VRF, third-party, and other building systems. This equipment can include indoor unit and outdoor unit compressor, mechanical ventilation equipment, auxiliary heat in colder climates, and additional safety controls. VRF sensors, controls, mechanical components, and other pieces of the VRF system are always in constant communication. The information that's made possible in a fully integrated VRF system includes personalized comfort for occupants, automatic adjustment based on the location and number of occupants in a zone, energy allocation, which we'll get into later, and centralized control for a facilities manager or a building manager. Facilities managers gain access to most system points to obtain peak performance when they use manufacturer-provided controls through the VRF system. Controlling supplemental equipment within the building can often require a higher level or more equipment and more attention by the VRF manufacturer themselves. A facility manager can then monitor up multiple zones across a building, set up operating schedules, and adjust equipment remotely. Varying levels of access are also possible depending on the system used. For example, one facility manager might have an enterprise view to allow for reporting, status, and master control of all systems, while others may only have access to a select number of systems or spaces. Some leading manufacturers in the VRF industry offer control software and non-proprietary platforms such as Tritium's Niagara framework. In this situation, VRF controls can integrate very easily with a third-party building automation system and third-party equipment. The most standard protocol that's used today is BACnet, though multiple open protocols are available and can be used. VRF manufacturers can provide the BAS for a building directly. The benefits of this would be optimal performance of the VRF system and efficiency. A VRF manufacturer who's involved throughout the entire process of the building through and ending with the controls can be a benefit. And if necessary, an advanced integration package can also be established to provide better overall control. A VRF manufacturer may also offer package controls that provide points that beyond what a normal VRF integration can provide over BACnet or LawnWorks. In general, a larger number of points and more detailed information for service and troubleshooting can be available when a package like this is used. So let's get into some of the specific systems and components that might be required when you have third-party integration, even if VRF is the main source of heating and cooling, as Kevin described. The first one we'll look at is mechanical ventilation. VRF systems inherently do not provide good ventilation or good dehumidification control. In this situation, a separate piece of equipment, such as a dedicated outdoor air system or an internal energy recovery ventilator, may be required. There are two styles of introducing ventilation air to the space: decoupled and integrated. An integrated system would have a packaged outside air unit that feeds air into the VRF unit that's accomplishing most of the heating and cooling within the space. In a decoupled ventilation scenario, you have both systems working side by side within the space, but the ductwork itself is not specifically attached. Those pieces of equipment, energy recovery ventilators and dedicated outdoor air systems, have several ways of communicating. Many industry standard manufacturers would use the same communication protocol as the VRF equipment, and integration in that situation is very easy. A third-party dedicated outdoor air system might be integrated with a simple input-output configuration, or it might come with a backnet card that makes most of the communication available over software rather than hardwired points. This can save a lot of integration time and a lot of actual physical labor on the job site as well. Let's look at a scenario like a large restaurant. VRF systems provide energy-efficient comfort, and fluctuating heating and cooling loads as a guest transitions from one space to another can be uncomfortable. However, even if the restaurant uses a DOAS to provide conditioned outdoor air to staff and guests, the amount of grease and debris produced by the commercial kitchen systems mean that a restaurant typically requires third-party packaged rooftops and makeup air units. A third-party mechanical ventilation system that natively uses different proprietary protocol and controls can be integrated with a VRF system through a simple input-output configuration. The same input-output configuration is used for a third-party DOAS that could then coordinate the operation of makeup air units and exhaust fans. A helpful integration tool for other scenarios like this is a linear expansion valve kit that allows the use of third-party equipment to be outfitted with a VRF coil. This is also a useful application in a retrofit situation where all third-party air handlers are now basically VRF systems, and all of the benefits of those systems would apply. Now let's talk about auxiliary heat. Contrary to past perception about heat pumps and variable refrigerant flow technology, these systems actually do extremely well in cold climate applications. As an example, city multi-hyperheating units are able to provide 100% of their rated heating capacity at -5 and up to 78% of that rated capacity down to -13 degrees outdoor ambient conditions. That said, for extreme temperatures that are below that threshold or even close to it, and I'm sure many people can remember the past winter's polar vortex in the Midwest, supplemental heat is definitely preferred by designers. Here's an application and an example of a VRF system with an auxiliary heat integrated through a VRF manufacturer's provided controls. VRF controls can be configured to activate backup heat when it's required in those extreme situations. As required by the application, The VRF controls can manage and sequence almost any kind of supplemental heating, including hot water baseboard or electric, into the ductwork to work as a backup and supplemental provider of heat in extreme situations. Now let's talk quickly about safety controls. I want to preface this section by saying that we are not talking about life safety components, which should always be done by a hard shutdown method per your local code. Especially in buildings with several points and systems that need to be integrated, safety monitoring is critical and may require additional equipment. Depending how the occupants use that space, it may require the use of third-party controls and third-party safety equipment. Let's look at an example. Uber's Advanced Technology Center, which was opened in the summer of 2016, used VRF as its main method of heating and cooling in the spaces. It's the main campus for Uber's autonomous vehicle research and development, and vehicles that were under testing were inside of its garage, side by side with conference room and office space. Monitoring cars' exhaust and fumes was a priority for the facilities managers. They needed a dashboard and a way to be able to monitor and control equipment that was used for the safety of the noxious fumes that were being put into the space by vehicles that were being tested. For this reason, VRF and DOAS systems were directly integrated through a Diamond Control Systems interface. Third-party CO2 and NOx sensors were installed throughout the system and throughout the building. DOAS and CO2 were integrated into that interface, which gave the facilities management team direct visibility to how the system was operating and to keep everyone in the building safe. You can read there a testimonial from TJ Wallowitz, who was one of the building managers responsible for the occupants' comfort and safety. Now let's talk about an instance where we had existing equipment and advanced integration and controls were needed. An educational facility, a technical college that purchased VRF systems for a new building on campus, had an existing chilled water system that was retained to serve the rest of the campus. In that scenario, VRF manufacturer provided controls provided integration between all systems on that campus, including a plant controller, air-cooled chillers, pumps, and the VRF system that was going into the new facility and campus dorm. The VRF system was configured to manage the chilled water loop in addition to the VRF system, and the temperature differential between the water and supply water set point was assessed by the VRF system. I hope this promoted some questions and that we can have a discussion at the end of today's presentation. If you had any questions about the technical details that we just discussed, please feel free to log them in the questions section now. And now I'm going to turn the presentation back over to Kevin, who's going to close it out for us. Kevin?
Thank you, Tom. That was a very insightful and detailed look into the technology, including your overview of the types of third-party integration. I know we'll have lots of questions for you at the end of the presentation, and that said, here's another quick reminder to those on the phone to submit your questions using the Q&A function within the presentation interface. Now that we have an understanding of VRF technology at a high level and have peered deeper into its application with third-party systems, let's look at one more real-life example where applying VRF with third-party equipment resulted in superior energy efficiency and performance for a building. The Garrett Jacobs Mansion is located in Baltimore, Maryland. The building is a historic 4-story home built in the late 1800s, which is today used for weddings, banquets, and events. The celebrated building, preserved by state historical easements, has been home to the Engineering Society of Baltimore, or Engineers Club, since 1961. A few years ago, the Engineers Club realized patrons required more accessibility to the upper floors of the mansion, as well as a streamlined and updated HVAC system. The building has several types of conditioning systems, including outdated boilers, which led to inefficient operation and an inability to satisfy the venue's comfort requirements. When the club decided to expand and build an adjacent 5,600 square foot addition, the time was right for a new HVAC system. The solution to their HVAC challenges was a system comprising of variable refrigerant flow, loss and energy recovery ventilators, and a central controller to which all equipment was tied in. The project was designed and engineered by Spears, Vada & Associates. According to Corey Colassard, Vice President at Spears Vada, quote, "This project is an opportunity to improve the building, improve operating costs, give the Engineers Club flexibility, and allow them to have individual temperature control in multiple rooms. It's an improvement that's generating a master plan for moving forward instead of putting a bandage on the conditioning issues as they arise." The combination of VRF, ERVs, and a centralized control system was a win for the Engineers Club overall, making their space an inviting one for years to come. Before we get to questions, there are a number of takeaways we would like to leave you with after today's presentation. Those include, number one, VRF is emerging as the preferred energy-efficient heating and cooling system in the United States market. Number two, VRF systems are typically installed alongside other types of HVAC equipment and other mechanical equipment, as Tom talked about earlier today. Number three, there are many ways to integrate VRF technology into existing or new buildings. And lastly, that VRF manufacturer controls can make this integration seamless. The HVAC industry is ever evolving and will continue to do so into the future. METUS will continue to invest in developing new technologies that further advance that energy efficiency, design freedom, and installation flexibility of HVAC systems to meet and exceed the needs of the market. That concludes the prepared portion of today's presentation. On behalf of Tom Greco and the entire Mitsubishi Electric Trane HVAC US organization, we want to thank you for the investment of time you've made in today's webinar. We hope you were able to gain new knowledge on the ways to integrate VRF systems with third-party HVAC systems, and we want to leave plenty of time for you to ask your questions this afternoon. On the screen, you'll find a number of resources available for your use after today's presentation. These resources include our website, www.metahvac.com, a link to subscribe to our quarterly newsletters, and a link to the case study that we discussed today. With that, I'll now turn the floor over to Andy to close out the presentation and open it up to the questions that have been asked today. Andy?
Thank you, Kevin, and great job, gentlemen. So we have a number of questions that have come in, and they cover a lot of different ground, so let's just get started. So to begin, there was a question with regard to our mention of energy allocation. So someone asked, can you talk more about energy allocation and how to set it up? And can you only get information about VRF systems, or can you get info on other equipment too?
That's a great question. Allocation of energy, there's many terms that are out there in the industry, and I'll say a few comments and then toss it over to Tom for the details from his perspective. Allocation of energy is very important in certain applications where you want to make sure that those that use or consume the energy are properly, that the utility is properly billed to them, so it doesn't become the burden of the building owner overall. Tom, when you think about energy allocation, I know that you've worked with it on a regular basis. What's your take on that conversation?
Yes, of course. So it's a great question. So I'm going to cut it into two parts. So energy allocation, what is it? Energy allocation is an inherent way that the system is monitored through the central controller, and the central controller is the piece that the VRF manufacturer would make that has an idea, we'll say, to keep it simple and not get into too many of the technical details. It has a feel for what systems and what indoor units that are attached to the system, how hard they're working, how fast their fan is running, how wide open their linear expansion valve is. And it takes that information and it essentially apportions a percentage of the work being done mechanically within the system. And then it takes that apportionment value and in concert with an energy meter that's attached to the outdoor unit and its power feed, it then apportions an electrical use to every system or every group of systems within a building. So like Kevin mentioned, you have a tenant, tenant A, tenant B. It can take a consumption of energy based on those calculations for tenant A, and it can actually output a percentage of the total energy use that tenant A has used versus tenant B. So that's how it works. When the question comes up about integrating the apportionment of other systems outside of VRF, the answer is yes, we can absolutely do that, but you would require a system like a Niagara platform or another industry standard protocol and control system to be used that would gather both the energy apportionment, the energy allocation that's done by the VRF system, and then the energy use that is completed by that third-party piece of equipment. It might be pumps, it might be air source chillers, you name it. The energy would have to be consumed, and then it can be aggregated and displayed either in reports or on a dashboard for the user's benefit and for the understanding of the energy use. Oftentimes, this then gets parlayed into tenant billing or tenant apportionment, as we call it, to show which tenants are responsible for which energy bills. Did that hit both points of the question? I think it did.
It definitely did. Great job. All right, let's move on to the next one. Unrelated topic, but I think you can handle it. So, how can I avoid installing two control networks, one for VRF and one for my DOAS terminal boxes, CO2 sensors, and DOAS air handlers?
That's a great question. Obviously, nobody likes to walk into a room or a behind the scenes in a maintenance room and see 3 or 4 boxes on the wall. Tom, there's many common programming languages that we can and other VRF manufacturers can integrate into that allow you to minimize that, correct?
Yeah, that's absolutely correct. You heard during my presentation I mentioned BACnet. BACnet has sort of become the standard, and especially in the eyes of ASHRAE, has become sort of the standard protocol on which our industry communicates. It's a 2-wire communication over an MSTP wire, and it can also be an IP communication over a standard Ethernet cable. Once you're in this world and in that protocol, you can essentially move between technologies and move between platforms pretty easily. Almost all building automation systems and building management systems have the capability within that type of network. When it comes to the terminal devices, CO2 sensors, humidity sensors, central controllers that would live on a VRF system, you need something to pull them all together, and avoiding pulling multiple networks becomes possible because you're now on that main trunk. You're in that main and common protocol like a BACnet. So what's happening in our industry is not only are the larger package systems, rooftop units, chillers, VRF systems, not only are they becoming BACnet enabled, but smaller devices, CO2 sensors, wall controllers, wireless wall controllers, application controllers that used to need a network are now becoming wireless. They're becoming enabled to take part in that open protocol like BACnet. So yeah, you're quickly getting to the point where you don't need to run or have multiple networks within a building. You're able to just survive in that one platform. And then, as we all know, to expand on it, is the next stop is the cloud, right? Everyone is trying to get to a platform that is then easily accessible up and down to a cloud infrastructure where you're then able to have users log in remotely and analyze and control and monitor their building from a cloud platform as we're seeing the industry move. So, yeah, absolutely.
Okay. So we have a few questions that have come in with regard to LEV kits. So we'll start with one of the more basic ones. Can you give examples of where LEV kits, linear expansion valve kits, were used on existing equipment?
Yeah, that's I'll call it a simple but unique innovation that allows somebody to take an existing air handler, let's say, tie in a VRF condensing unit, take advantage of the efficiencies that come with the inverter compressor without necessarily ripping out a whole bunch of other or ancillary equipment on the roof of a building or next to a building. Tom, in your work, do you recall any specific examples where an LEV kit might have been utilized to either get that efficiency or avoid some of that cost?
Yeah, absolutely. So the largest cost for a retrofit like that would be, the ripping and replacing of a giant piece of equipment. You need a crane or a helicopter or something, that's incredibly expensive, and logistics and cost and shutting down a road. Yeah, for sure. Instead, the internals of an existing or retrofit piece of equipment can essentially be replaced by and I've scrolled back to the LEV kit slide. You can see here, the box on the top, the silver box, is the controls, right? The brains of how it works. And then the LEV kit itself, you can see it's incredibly small, and one end of the pipe goes to the coil, and it's pretty easy to retrofit and commission in the field to turn an old chassis, if you will, into a modern air handler that takes the benefit of a VRF outdoor unit that would be placed somewhere else, either on the roof or in the building. So incredible advantages to retrofitting an existing piece of equipment with a modern VRF coil, and then using this control box to control things like mixed air dampers and fans or VFDs in the unit itself to turn essentially an outdated unit that needs replacement into something new and modern and very efficient.
Wow. No, you inadvertently answered a number of the other questions that came in on the same subject, though. That's pretty good, nice and efficient. Let's switch back to controls. So
just like a VRF system, right, Andy?
Exactly.
Yeah.
That's inverter-driven question answering. So here's the next one. Are advanced integration packages standard options, or are they completed custom for each job? How would I recommend the advanced package spec to an owner or consulting engineer?
Yeah, I think the short answer I'll give, and I'll let Tom, obviously, is the smarter one when it comes to this subject, give the longer answer. It depends. It depends on the needs of the project. It depends on what somebody wants to get out of the integration, and then how complex it is. I know, Tom, you've probably seen fairly simple, one or two pieces of equipment, and you've seen some fairly complex, larger buildings, different types of mechanical systems, all in one package. So if you expand on the "it depends," that probably makes most sense.
100%, right. So let's take a couple of examples. So a building, standard office building, using VRF, occupant comfort is the priority. Each space has its own system, its own indoor unit, not its own system, but its own indoor unit. There is let's call it, a simultaneous heating and cooling system like Kevin described to us earlier. Every room has its own thermostat. There is ventilation there that's decoupled and controlled on its own. And the owner says, yep, let's keep it simple. Let's not do anything crazy, but the building automation system has to have visibility. A standard integration package that's just a license on a central controller is probably enough. That is something that there's no reason to overthink it. There's probably 25 to 30 control and monitoring points of information that would come out of a standard license and be available to the building automation system that's on site. It doesn't matter who provides it. That standard integration license is going to be enough to get the job done. Let's take our example of Uber here. I put back on the screen Uber's Advanced Technology Center. There is no way to have an off-the-shelf price for this project. There were destratification fans in the garage bays that were controlled on VFDs. There was a laser cutter that had its specific ventilation that was used in one of the shop areas. There were huge areas served by big ducted VRF units. There were small conference rooms and phone rooms with little wall mounts. There were CEO level suites and conference spaces that needed their own touchscreen control. There was a CO monitoring and ventilation system that was tied together. All of this needed to be integrated and work in concert, and then an interface needed to be provided to the building manager to be able to see and control all of it. And I'll go way back to the beginning of our presentation here to show you what that interface might look like. So what you're seeing on the screen here is a floor layout, and this is the temperature view, but it could also be changed to show the ventilation view or the occupancy view or the, and if they had energy use monitoring, which Uber did not. But a building that had energy use monitoring, you could switch to the energy use layer and get a snapshot of how much energy is being used per wing or per floor, depending on how your building's laid out. So it was a very long-winded way of describing, yes, the it depends. So there are some integration packages and some options available that are off the shelf and have a defined part number and price. And then a situation like this is absolutely, you get involved with us or a VRF manufacturer who can outline a scope and understand what is needed and then provide the parts and pieces, the programming, the engineering, and the on-site assistance for the contractor to implement something like this. So definitely depends, but all options are available.
Okay, great. So this next question is a change of gears. It's dealing with installation and really the state of the industry. So here goes. How do you ensure that VRF technology is installed correctly? One of the drawbacks of VRF is due to a lack of education with maintaining the system as well as installing this technology properly. Are there certifications for contractors to look out for when selecting installers?
Yeah, I think training and installation, no matter who you talk to in the HVAC industry, whether it's a VRF manufacturer, a component supplier, a non-VRF, other type of HVAC manufacturer, the competency, skill level, and training requirements of the industry, they need to go up. I think there's a lot of room for improvement across the board. Speaking from our perspective, we make sure that any system that a contractor buys from one of our distributors or our partners to install, that distributor or partner makes sure that that contractor's been through our training course. We do not allow a contractor who has not been Mitsubishi Electric trained to purchase the system and install that system. And that's for the most part to avoid some of the headaches that come with the complexities of the system. I know, Tom, in your background, you've worked for us, you've worked for other HVAC manufacturers as well. There's a lot more electronics now inside of the system, which make installation a bit more complex than it might have been in the past. But at the end of the day, I don't believe, and I'm interested, Tom, in your perspective, that a VRF system is overall that much harder to install once you've gone through the training courses.
No, you could easily, and that's correct. You could easily argue that it's easier. My background is in commercial automation and commercial HVAC with buildings that had so many systems and so many different ways that a building or a space is heated or cooled. And if the system is designed properly and the footprint and the layout promotes a VRF design or takes advantage of a VRF design, it can actually be a lot more simple than a conventional system using hydronics or using fossil fuels. It can be a lot easier. back to the question on how do we ensure the quality of the installation. I mean, I'm sitting in an office building outside of Boston right now that has a giant training facility where we train contractors, we train engineers, we train design, build, and specifying engineers and contractors and architects on the systems. They're here, they're live, they're running. We have hundreds and hundreds, possibly thousands of people come through this training center every year to get certified on the proper techniques and gotchas, if you will, to installing a VRF system properly. And once you learn them, it's, I would argue, a less complicated task to put in a commercial VRF city multi-system, or any manufacturer for that matter, into a building. I think it's just, there's this misconception that it's overly complicated or something that people don't understand, when the actuality of it is it's just not using or burning fuel, and it's not moving water, and it's not moving a significant amount of air. It's moving refrigerant through refrigerant pipes, and it's just a different architecture. But controls, in my mind, are exceedingly simple, and how you connect to them is only becoming more advanced and moving further towards the cloud and remote access and connectivity. I think that's accelerating very quickly. So interfacing and controlling these units and visualizing and analyzing the systems when a VRF VRF equipment is put into a building, I believe is going to only become easier.
I'll add one more thing, Andy, before I toss it back to you for the next question. To play on the how do you ensure the quality of the installation, make sure it's in the engineering spec, that a contractor has gone through manufacturer's training. All manufacturers do training. They give a certificate of some kind at the end that says this manufacturer has been to the class, they've been hands-on with the equipment, they've worked with it. Make sure that something along those lines is in the spec, and that will guide you to the manufacturers who put more of an emphasis on training than others. Not everybody does, but it will guide you to those that really want to ensure the high quality of their installations.
And I'm, Andy, before you take it back, going to piggyback one more time and mention that Mitsubishi, as well as other VRF manufacturers, are offering factory direct services, factory direct commissioning and startup assistance, and factory representatives and factory direct personnel are available to ensure the quality of that installation in the event that a contractor or an on-site person just isn't comfortable. That's something that's absolutely offered and can be attained pretty easily in this market, no question.
Okay, great. All right, so this next question, Tom, you kind of touched on this earlier. What kind of information will I see for third-party equipment in VRF controls? Can you describe the interface?
Tom, I'll let you jump right in on that one.
Yeah, of course. I'm going to refer back to the slide that's live now. You can see in the, it's a little difficult to see, and if I apologize, but on the left-hand side there is a tree of information, and your visualized information in front of you is a floor plan layout that's specific to a building, right? That would be done in a 3D visualized way. But on the left, you'll see a tree of information, and what you would do is you would expand down, similar to clicking through folders on your PC or your laptop, and it would expand down and show you the number of pieces of equipment that are within a building. So let's take a rooftop, for example, that has nothing to do with Mitsubishi Electric. Let's say it's a third-party rooftop that has a BACnet-enabled control board. That unit would probably have 30, 40, 50 points of information that would be flowing over that and through that BACnet interface, and we would be able to pick up and display and control the unit based on all 50 of those points. Now, not every manufacturer has an expansive list of control points, but most of them do. The more complicated the piece of equipment, a large centrifugal chiller, a large air-cooled chiller, large boiler systems, those are going to have a lot more information, and we could make the graphics and the interface for the user as expansive or as simple as possible. I've seen several interfaces where there's just text. Is it on? Is it off? What's the set point? What's the threshold? What's the offset? And then I've seen systems where it's so complex as to completely visualize the entire unit. The whole unit is laid out in a visual manner where the points are actually placed on the unit based on, their position, like a valve would be shown, and right on the valve it would say open, closed, or have a percentage. There'd be a value right on the fan to show CFM or percent, percent of power that's being used. You can get really involved depending on what the need of the building is. So the answer is it depends, but I hope I gave some clarity to what might be available.
Yeah. I think that answers the question. Move on to the next one. So with regard to changeover functionality. So how does the changeover functionality work on a VRF heat pump system during shoulder months? Are there built-in factory deadbands between heating and cooling?
It's a great question and a common one. I think for most of the country, we're either in or nearing the end of our shoulder season. I know down here where I am in Atlanta, it can't make up its mind whether it's hot or cold, so we're fluctuating between both. I think it might be the same up for you, Tom, or even on the colder side. So what do you typically see in some of the buildings that you work in across the country?
You could do a 4-hour presentation on this topic, but I'll try to be brief here. When you have a heat pump system, and I think the question was based on a heat pump system or a non-simultaneous VRF system that does not have the ability to simultaneously heat and cool from the same refrigerant circuit, there's a few options. One of them is to just strictly schedule the unit. You can schedule the unit to say we are in heating at this time of the year, we are in cooling at this time of the year. This sets expectations and allows the occupant to know, okay, at this time of the year I'm getting this time of the year I'm getting this, and a manual button push, if you will, has to be done in order to change it on a unique day. A day in May where it's incredibly cold, or a day in a day towards the end of the springtime where it just becomes incredibly warm and you need cooling. The other answer is that you can use advanced controls and a control package that was created and put on by the VRF manufacturer. Mitsubishi does have one such program where it's actually monitoring the load that's required and the call from the indoor units, and it can decide based on almost a voting system whether or not the outdoor unit should be in the heating mode or the cooling mode. What it also will do is, if there is a call for both, it will provide those votes, and then it will maintain the heating mode for a specific amount of time, and then switch over to the cooling mode. And it will go back and forth based on the need. And in an efficient building, that is, the envelope is tight and is able to hold the thermal dependency of whatever you've provided to that space, we've actually found that it can really keep the occupants very, very happy, even in a non-simultaneous scenario. So the answer, again, is depends on the situation, but there are multiple methods to control changeover, and those methods are actually growing and being fine-tuned on a daily basis, because let's just face it, the simultaneous systems, they do have more components, and they are typically more expensive. So the changeover method for a non-simultaneous system continues to be a large topic for us on the control side.
Okay. Next question. This is with regard to backup heat or auxiliary heat. How often do you have to run auxiliary heat if you use VRF in a cold climate? Wouldn't running the auxiliary heat lower your overall energy efficiency?
It depends on a number of factors. I would say it depends on the nature of the cold climate zone. Cold could be Kentucky or cold could be Maine. it depends on the needs of the building and the application itself. VRF systems, if you put in the hyperheating or other brand names that might be out there, which are the high-performance heating brands, they have guaranteed performance in some cases down to minus 22, 21 degrees Fahrenheit, and they operate down to call it minus 31 Fahrenheit in some cases. So the systems will pretty much run in most of the cold climates or the worst polar vortexes that we've seen. Obviously, if you get below minus 22 outside and that guaranteed performance goes away, that's when you might consider backup heat, or even at some point before that. Tom, in your experience, you've worked most of your career up in the Northeast. What do you see in terms of, one, the integration of backup heat, and then two, to the question about lowering the overall efficiency of the system?
Right, both great questions, and that's a good way to slice them apart. So first of all, the integration of backup heat can be done very easily, and in most cases without anything advanced or special. So that's the first thing. So let me push back to my integration slide here. So this is probably the most involved setup of backup heat that you could possibly have. There are several scenarios where the indoor unit itself, which you see on the bottom there, the wall-mounted indoor unit, or a ducted unit, or a ceiling cassette VRF type unit, would actually have a contact on it that would provide the on and off signal to an auxiliary source of heat. That's something we see that's very, very common. Then we get into scenarios where they want it integrated a certain way, or to only work below a certain temperature, or to only enable when the outdoor unit is, completely maxed out, or to only enable when the temperature offset from the desired temperature to the actual temperature in a room is X. So I just described a lot of different scenarios of how a customer or how a designer wants that auxiliary heat to work. And in that situation, you might need something like what's on the screen here and have the advanced programming and sequencing to accomplish all that and make it happen. A comment on the overall efficiency. So if your backup is a gas-fired furnace, gas force hot air, and it's incredibly cold out, I'm talking extremely cold out, that outdoor unit might have more than enough capability to provide heat to that space, but its overall efficiency based on the outdoor air temperature is going to go down. That's just thermodynamics. That's going to happen. If at that point your forced hot air unit is then, just by default more efficient because of the cost of gas per therm, then in that scenario and the sensing that's done by your VRF BAS system determines, well, it's more efficient for you to run this source of heating than the heat pump, then yeah, you would have a system that's making that decision for you. And we have several options that can help you make that decision. One of them was mentioned in this presentation, Diamond Controls. Another one is a system that we have called Kumo Station. So, and other manufacturers, I'm sure, have their options as well. So there are ways in which you can choose between using the heat pump in an extreme temperature situation and converting to, or enabling, I should say, a secondary and auxiliary source of heat. And your efficiency numbers would then play into that.
Andy, I want to be cognizant of everyone's time. I know we're coming up on the hour here, so I want to just make a quick closing comment. Thank you, Andy, for moderating that Q&A, and Tom for your insight as well. To those of you that are on the phone and have joined today, thank you very much for your time. We hope it was valuable on behalf of our entire organization. We hope you took one or two things away with you today. If we can be of any help to you in the future, please do let us know. As you can tell, we're pretty passionate about VRF controls integration, and we want to see this product continue to grow with its share of the market here in the United States. So thank you all very much. Have a great rest of your afternoon, and we'll talk to you soon.